3i Atlas was emitting this emerald green color. Some people are picking up on different things onto 3i Atlas and what this could be.
Comets usually follow a pattern. This one, not even close. 3i Atlas just showed up glowing green. And no, it's not the usual dicarbon glow we see in comets. Its chemistry's weird, its color makes no sense, and it's changing faster than anyone expected. Scientists are baffled, and yeah, they're watching this thing very closely. So what's going on here? Let's break it down. A coma that breaks the rules. When comets enter the inner solar system, their behavior is normally predictable. The sunlight heats them, water ice sublimates, and a coma forms around the nucleus, while a tail streams out away from the sun under the push of radiation pressure and the solar wind. That's the classic pattern, and we've seen it countless times in solar system comets. But with 3i Atlas, the rules are broken right from the start. By August 2025, the Gemini South Observatory confirmed that 3i Atlas had developed an anti-solar tail over 35,000 miles long, proof that its activity was vigorous and consistent with ordinary cometary mechanics. But that wasn't the whole story. Astronomers quickly noticed something strange close to the nucleus. The inner coma appeared elongated toward the sun. At first glance, this looked like a paradoxical anti-tail, a feature pointing in the wrong direction. But deeper analysis revealed it was actually a sunward dust plume. Here's how that works. Normally, sublimating gases carry dust grains outward, and radiation pressure soon pushes them into the anti-solar direction. But in 3i Atlas, the heating on the sunlit hemisphere was so intense that jets of dust were blasting directly toward the sun before the solar wind bent them backward. That created the illusion of a comet, defying the solar breeze. This is rare in comets we know, and it signals that 3i Atlas has localized vents that switch on powerfully when illuminated. By early September 2025, this odd sunward elongation reshaped itself into a broad, fan-shaped inner coma. That transformation told astronomers something crucial. The activity on 3i Atlas was not static. It was evolving rapidly on week-to-week timescales. Instead of a stable set of jets, the comet's outgassing was intensifying, spreading, and possibly opening up new fractures or vents on the nucleus. This rapid evolution is unusual. In solar system comets, activity tends to ramp up more steadily as they approach the sun, driven primarily by water sublimation. But in 3i Atlas, the coma seemed to reorganize itself almost overnight. One week, it looked like a narrow sunward plume. The next, it fanned out like a sheet of dust, implying that different layers of the nucleus were being accessed and that the balance between gas and dust production was shifting dramatically. For astronomers, these morphological quirks are more than just pretty patterns. They serve as diagnostic tools. By analyzing the geometry of the tail, the brightness layers within it, and the changing shapes of the inner coma, scientists can reconstruct the rotation of the nucleus, the location of active regions, and the distribution of dust sizes without ever seeing the surface directly. In the case of 3i Atlas, the unusual fan-shaped coma is essentially a live blueprint of the comet's hidden activity. To put it simply, the coma of 3i Atlas is a rule breaker, and instead of evolving gradually, it shifted its entire inner structure in just weeks. This kind of behavior tells us we're dealing with a comet that is physically unstable, chemically unusual, and far more dynamic than anything in our backyard. What makes 3i Atlas fascinating is not just that it's active, but that its activity is wildly unpredictable, giving us a real-time lesson in how alien comets behave when they meet our sun. A dominated comet. When scientists train the James Webb Space Telescope, the Very Large Telescope in Chile, and the Gemini South Observatory on 3i Atlas, the data revealed something no one expected. This comet is built on a chemical recipe unlike any comet native to the solar system. Instead of being dominated by water ice, its spectrum showed an extraordinary dominance of carbon dioxide. The measured ratio of CO2 to water was around 7.6 to 1, an order of magnitude higher than in typical comets. Why does this matter? CO2 sublimits at far lower temperatures than water. On Earth, we call it dry ice, and even at room temperature, it evaporates directly into gas. In space, that means a comet dominated by CO2 can start releasing gas and dust much farther from the sun than a water ice comet. That fact alone explains why 3I Atlas became active earlier than expected, long before reaching distances where solar system comets normally wake up. Its surface chemistry has been driving activity since it was still in the colder outer reaches of the solar system. But the CO2 dominance is only part of the story. Observations also suggest the nucleus of 3I Atlas is covered by a thick, insulating crust. This crust acts as a lid, trapping water ice deep below the surface while allowing CO2 to escape through cracks or weak points. The result is a delayed water signature. While ordinary comets quickly show water vapor once they approach the inner solar system, 3I Atlas has stayed mostly dry on the surface, even while pumping out huge amounts of CO2 gas. This crust may be several feet thick and could represent billions of years of cosmic ray processing and thermal evolution, sealing water under layers of hardened carbon-rich material. Adding to the mystery is its metal vapor chemistry. In solar system comets, astronomers routinely detect trace amounts of nickel and iron together. They often show up in similar proportions because both metals exist in the dust grains that outgas when heated. But in 3I Atlas, while nickel vapor has been clearly detected, iron is conspicuously absent. That asymmetry is highly unusual. It may mean the comet formed in an environment where iron-bearing minerals were less abundant, or where iron condensed out in a way that prevented it from being incorporated into the outer layers. Either way, it marks 3I Atlas as a product of a different kind of planetary nursery than our own. Bulk measurements make the picture clearer. Based on its brightness, activity, and gas output, scientists estimate that the nucleus of 3I Atlas is about 3 miles across and weighs roughly 36 billion tons. That puts it in the same size class as many mid-scale comets of our solar system. But despite looking familiar in size, it is anything but familiar in composition. Its mass is wrapped up in volatile CO2 ices, locked in deep water layers, and strange metallic chemistry, making it a comet built from alien ingredients. The implication is profound. 3I Atlas likely formed beyond the CO2 ice line of its parent star, a region colder and farther out than where Earth's comets typically formed. In a protoplanetary disk, different volatiles freeze out at different distances. Water ices freeze closer to the star, CO2 farther out, and exotic ices like nitrogen even farther. For a comet to be so carbon dioxide rich, it had to assemble in a part of its star system where dry ice was stable, suggesting its birthplace was in the outermost regions of that system, or that it was a fragment of a larger icy body, similar to a dwarf planet. The green glow nobody expected. When amateur astrophotographers Michael Yeager and Gerald Riemann aimed their telescopes at 3I Atlas during the lunar eclipse of September 7, 2025, they captured an image that shocked astronomers worldwide. The interstellar comet, already remarkable for its unusual activity and strange composition, appeared to glow a brilliant emerald green. The photographs showed a luminous coma with a distinct green hue, tinged faintly with blue at the edges. This was not just another pretty picture. It was a scientific puzzle that cut to the heart of how cometary light works. Why is this so strange? In our solar system, the appearance of a green comet is usually a straightforward story. The glow comes from dicarbon molecules. When exposed to ultraviolet sunlight, these molecules absorb energy and re-emit it in the visible spectrum as the bright swan bands, which fall in the green part of the spectrum. That's why comets like Lovejoy or Neowise have appeared green when they passed through the inner solar system. The process is well understood. But here's the catch. Spectroscopic studies of 3I Atlas conducted in late August and early September 2025 revealed something completely different. This comet is severely depleted in carbon chain molecules. Specifically, it lacks dicarbon, the very compound responsible for green Comet in solar system comets. Scientists expected its coma to look reddish, dusty, or even neutral, but not green. In other words, 3I Atlas was putting on a light show using ingredients we don't fully understand. The mystery deepened when some outlets, and notably Harvard astrophysicist Avi Loeb, suggested that the green glow might be explained by cyanide. CN has indeed been detected in 3I Atlas, so on the surface this might sound plausible. But spectroscopy doesn't lie. Cyanide glows in the violet and near ultraviolet, with its strongest emission at around 3,870 angstroms. It also produces weaker lines at about 4,200 angstroms. Both of those are too far blueward to explain a bright green emission. In fact, studies as far back as the 1990s demonstrated that CN cannot account for green cometary colors. So, if not cyanide and not dicarbon, then what? Several candidates are being discussed among astronomers. Oxygen atoms can emit a bright green auroral line when they are excited into a special high-energy state. This sometimes occurs when water or CO2 molecules are broken apart by solar radiation. Another carbon-based radical, C3, emits in the blue-green region and can sometimes appear in cometary comae. However, it is typically faint and normally accompanies dicarbon, which is missing here. Ionized carbon monoxide can also glow in the blue-green part of the spectrum. Given that CO2 dominates 3I Atlas and some CO is present, this pathway might become important as the comet gets closer to the sun and solar UV radiation intensifies. Sometimes the impression of color isn't only about emission lines. A cloud of small, clean, icy grains can scatter sunlight in a way that skews toward blue-green wavelengths. This would not be an emission process, but rather a scattering effect, still capable of producing a coma that looks green to both cameras and human eyes. At present, the truth is that no single explanation fits perfectly. The comet's green glow is likely a combination of multiple processes, perhaps a mix of faint oxygen emission lines, scattering from freshly ejected icy grains, and contributions from rare radicals. Whatever the case, the one thing that is clear is what the glow is not. It is not dicarbon, and it is not cyanide. That fact makes 3I Atlas a trailblazer in cometary science. It is the first interstellar comet observed to glow green without the usual culprit. Its emerald hue forces astronomers to consider new pathways of chemical excitation in an alien environment. More than just an aesthetic twist, this phenomenon is an open question in astrochemistry, and it ensures that the comet's nickname, the Green Interstellar Visitor, is likely to stick in the public imagination. For astronomers, though, it is not just about color, it is about evidence. By carefully tracking the glow as the comet nears perihelion and comparing spectroscopic fingerprints, researchers hope to finally pin down the true source of the green. Until then, the comet's light remains one of its most beautiful and most perplexing mysteries. A comet that changes its colors. Comets don't usually act like traffic lights. Yet, in the short span of a few weeks in 2025, 3I Atlas seemed to do exactly that, shifting from red to white to green. Each stage reflected a different phase in its physical evolution as sunlight peeled back layers of its alien surface. While the dramatic green emission has drawn the most attention, the earlier red to white transformation is equally important because it reveals the hidden structure of the comet's surface and coma. When astronomers first observed 3I Atlas in July 2025, its coma appeared distinctly red. A red coma is typically caused by dust particles that scatter sunlight with a reddish slope. These grains are often coated with organic residues and have been altered by cosmic ray exposure over billions of years in interstellar space. In other words, the redness was a fingerprint of its ancient history, a surface weathered into a dark, carbon-rich crust. The light reflected by these dust particles leaned heavily toward the red end of the spectrum, making the comet appear rusty or brick-colored. But something dramatic happened as the comet moved closer to the sun. By mid-August 2025, the red glow began to fade. In its place, astronomers started reporting a coma that looked whiter, brighter, and more neutral in color. This was not a coincidence. The surface crust that had been dominating the light signature was being overpowered by newly released icy grains erupting from beneath. These small grains scatter sunlight far more efficiently and reflect it in a way that appears white or even slightly bluish. Essentially, the comet had started to shed its aged outer skin, revealing a fresher, more reflective layer underneath. Data from the Atlas telescope network captured this change in measurable terms. At distances beyond 3.3 astronomical units, the comet's brightness increased very steeply, following a power law. This steep slope indicated that the reflected light was still dominated by reddened surface dust. But once the comet came closer than 3.3 astronomical units, the curve flattened dramatically. That sudden change suggested a shift in what was causing the brightness. Instead of reddened dust, the coma was becoming dominated by optically bright, icy grains. It was a clear, quantitative sign that the comet's activity had entered a new phase. This shift is scientifically significant. The progression from red to white shows that 3I Atlas has a layered structure. The outer surface, processed for eons, is dark and organic-rich, but beneath it lies a fresher layer of volatiles capable of releasing clean ice particles. As solar heating fractured the crust, these grains erupted outward and began to dominate the coma's light signature. It's the cometary equivalent of peeling away a burnt crust to expose the frozen core beneath. The change also highlights the comet's fast-paced evolution. In many solar system comets, the transition from a dust-dominated coma to an ice-rich coma happens more gradually. But 3I Atlas seemed to flip its color palette in just a matter of weeks, which suggests that the insulating crust was not just passively eroding. It was breaking open in sudden events that released large amounts of trapped volatiles at once. It demonstrated that the comet carries a complex stratigraphy with different color signatures marking different epochs of its life story, polarization, and Pluto-like clues. When light from the sun strikes a comet, it doesn't just scatter randomly. The interaction between light waves and dust grains can cause the light to become polarized, meaning the vibrations of the light waves align in certain directions instead of being scattered equally. By measuring this polarization, astronomers can infer properties of the dust grains, their size, porosity, composition, and even whether they carry thin coatings of frost or organic material. Polarimetry is like an X-ray for cometary dust, and in the case of 3I Atlas, the results were startling. Observations with the Nordic Optical Telescope showed that 3I Atlas exhibited an extremely deep and narrow negative polarization branch. That phrase sounds technical, but it refers to a very specific behavior. At small phase angles, when the comet is seen almost directly opposite the sun, the scattered light becomes polarized parallel to the scattering plane, rather than perpendicular. Most comets show this effect to some degree, but in 3I Atlas, the depth of the negative branch was far stronger and the angle much narrower than usual. This isn't just a quirky detail. It points directly to the microphysics of the comet's dust grains. Laboratory experiments have shown that such a polarization signature can be produced when grains are made of dark, carbon-rich material coated with a thin layer of water ice. The frost changes how light interacts at the grain's surface, enhancing coherent backscattering and shadow-hiding effects, which drive the negative polarization deeper than in bare dust grains. In other words, the grains in 3I Atlas's coma appear to be frosted soot particles, dark cores wrapped in a thin skin of ice. That combination is unusual, but not unheard of. In fact, it resembles conditions on some of the most distant objects in our own solar system. Trans-Neptunian objects like Pluto and its moon Charon have shown polarimetric behaviors that align with surfaces covered in volatile frosts over darker substrates. On Pluto, for example, nitrogen and methane ices condense seasonally over a dark, organic-rich base. On Charon, thin coatings of water frost sit atop older, darker material. The resemblance to 3I Atlas suggests that it too may have originated in the far outer regions of a planetary system, where cold frosts and dark organics coexist. What makes 3I Atlas stand out is that we're seeing these frosted grains not on a surface, but in the coma itself. That implies the nucleus is releasing fragments that still carry intact frost layers. As they sublimate and evolve in space, those frosts alter the way sunlight scatters off them, leaving a polarization signature that is unique and diagnostic. This also ties in with the comet's rapid transformations. If different layers of the nucleus are exposed at different times, the composition and frostiness of the ejected grains may shift, changing the polarization signal in measurable ways. Polarization is not about which molecules fluoresce or how grains scatter sunlight across colors. It is about the directional alignment of light waves after scattering, and it probes features invisible to color measurements. That makes it an independent tool for decoding the physics of alien dust. Spacecraft eyes on an interstellar visitor. By the end of September 2025, astronomers faced a frustrating reality. 3I Atlas was sliding too close to the Sun for Earth-based telescopes to follow. From our perspective, the comet would soon be hidden behind solar glare, and later completely lost during solar conjunction. But just because Earth loses sight doesn't mean the story stops. In fact, this is where a fleet of spacecraft across the solar system steps in to keep watch. Between October 1st and 7th, 2025, the European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter had a front-row seat as 3I Atlas passed within about 19 million miles of Mars. That might sound distant, but on a cosmic scale, it's relatively close. From Mars orbit, these spacecraft were positioned to view the comet's sunward side, the hemisphere that Earth telescopes couldn't see because of the solar geometry. This gave them an invaluable perspective on how gas and dust jets were forming and evolving at the very moment Earth observers were forced to go dark. The data these missions can gather isn't just about taking pictures. Instruments aboard Mars Express and TGO are designed to analyze gas emissions, dust distributions, and ion interactions in planetary atmospheres. Repurposed for comet observations, they can track how 3I Atlas's coma responds to solar radiation and the solar wind. For instance, they can measure the onset of new gas species, monitor outburst activity, and follow how the coma density changes over hours to days. This type of continuous monitoring is nearly impossible from Earth when the comet is near the Sun. At the same time, NASA's Psyche mission en route to the metal-rich asteroid 16 Psyche also joined the campaign. Psyche wasn't launched for comet studies, but like other deep space missions, its instruments are versatile enough to capture valuable data. Positioned between Earth and the asteroid belt, Psyche observed 3I Atlas from a different angle, adding another geometric baseline for analysis. By combining data from Mars, Psyche, and earlier Earth-based telescopes, astronomers can triangulate features of the coma and tail, reconstructing their true three-dimensional structure. But perhaps the most critical role will be played by the Jupiter Icy Moons Explorer. Between November 2nd and 25th, 2025, JUICE is scheduled to focus its instruments on 3I Atlas during its perihelion passage, the point of closest approach to the Sun. This is the moment when comets become their most active and chemically revealing. Solar heat drives ice to vaporize violently, producing dense comae and long tails that act as chemical fingerprints of the nucleus. Why is JUICE so important? Because from Earth's perspective, perihelion is exactly when the comet is invisible behind the Sun. JUICE, positioned farther out in the solar system, has the right vantage point to catch what Earth cannot. Its instruments can measure the full spectrum of gases being released, including CO2, CO, water vapor, and trace compounds, providing a direct chemical profile at peak activity. If the comet's water subsystem finally turns on, JUICE will be the first to confirm it. If exotic ions like CO+ or radicals like C3 dominate, JUICE will see those as well. Together, these spacecraft form a relay of observers. Mars Express and TGO covering the early October phase, Psyche providing complementary geometry, and JUICE capturing the all-important perihelion window. What makes this remarkable is that none of these missions were launched to study interstellar comets, yet circumstances have turned them into an impromptu observing network. Their data will bridge the gap between Earth-based campaigns and the comet's eventual reappearance after conjunction in December 2025. For scientists, this is more than just a convenience. It is a rare chance to study an interstellar object from multiple vantage points at the very moment when it is most volatile. With spacecraft stationed around the inner solar system, 3I Atlas is giving us a coordinated experiment, a look at how alien ices behave under solar heating, observed simultaneously from different worlds, age, origins, and what comes next. One of the most compelling questions about 3I Atlas is not just how it behaves in the solar system, but where it came from, how old it is, and what will happen once it leaves us behind. The answers are still forming, but what scientists know so far points to a story stretching across billions of years and countless light years of space. The first clue comes from trajectory analysis. Using data from the Gaia spacecraft, astronomers traced the path of 3I Atlas backward in time. Over the past 4 million years, the comet has not passed close to any major stars. This means it has been traveling through interstellar space undisturbed, preserving its outer layers from gravitational encounters that might otherwise have altered its orbit. Beyond 4 million years, the uncertainties in orbital reconstruction grow too large to be precise. But the message is clear. This comet has been wandering alone for an extraordinarily long time. That solitude makes 3I Atlas a pristine sample. Its surface may have been altered by cosmic rays and interstellar weathering, but its core preserves the chemistry of the system where it was born. Current age estimates suggest it could be between 3 and 7 billion years old. Some models lean toward the lower end, around 3 billion, while others favor a much older age. Either way, it could easily predate the solar system itself, which is about 4.6 billion years old. In other words, this object may be older than Earth. Another oddity lies in its orientation. The trajectory of 3I Atlas is unusually well aligned with the ecliptic plane, the thin disk where the planets orbit the Sun. For an object arriving from interstellar space, this is statistically improbable. Analyses suggest that the chance of such an alignment happening by coincidence is only about 0.2%. What this means is still debated. It could be the result of a detection bias, since our telescopes are best at spotting objects close to the ecliptic. Or it might hint that interstellar comets are more likely to be ejected along low-inclination paths from their home systems. Either way, the geometry adds another layer of mystery. Looking ahead, scientists are also watching for near-term drama. In late September 2025, projections indicated that 3I Atlas would be struck by a coronal mass ejection, a powerful burst of solar plasma and magnetic fields. On Earth, CMEs create auroras, but for a comet, they can reshape its tail, strip ions, and trigger sudden outbursts of gas and dust. For a volatile-rich comet like 3I Atlas, the encounter is expected to be a natural experiment. We will see how alien ices and dust react when slammed by high-energy solar wind. Brightness ripples, tail disconnections, or even the exposure of new compounds could result. After this, the comet enters a period of invisibility. From late October to early December 2025, 3I Atlas will pass behind the Sun from Earth's perspective. When the comet reemerges in December, it may look very different. By then, it will have survived perihelion. Or not. Some comets fracture under the stress of solar heating, splitting into smaller pieces. Others endure, but with heavily altered surfaces. For 3I Atlas, survival is not guaranteed. If it does endure, the post-perihelion observations could be the most scientifically rewarding. As the comet moves away from the Sun, astronomers will get a second look at its coma and tail, potentially revealing the deeper layers beneath the CO2-rich crust. These layers may finally expose significant amounts of water vapor, long suspected but so far hidden. They could also show whether the comet's dust and ice ratios have shifted after intense solar heating. In the long term, 3I Atlas will not stay with us. Its orbit is hyperbolic, meaning it is not bound to the Sun. After this brief interstellar flyby, it will head back into deep space, perhaps never to return. But the data we gathered during its passage could shape our understanding of how comets form around other stars. Thanks for watching. If you found this strange, hit like and subscribe. Got a theory? Drop it in the comments. We're watching them all. More space mysteries coming soon.